Hello. In this video, we're going to talk about sequentially dense subsets of R and their relationship with dense subsets of R. Just to remind you, a subset of real numbers is called dense if there is an element of that set inside every interval. So if you take an interval A to B, there is always an element S inside S, and that's when we say the set S is a dense subset. Sequentially dense means every real number is the limit of a sequence in that set. But what does it mean for a sequence to be in a set? It means all of its elements are in a set. So intuitively, that's kind of like natural to think about it this way. So formally, we say a sequence AN is in a set S if and only if each term of the sequence AN is in S. And by the way, all of the definitions are in fact if and only if statements. Even if it's not stated as if and only if, they are all if and only if. By default, the nature of all definitions in mathematics is that way. So the next definition is the definition of sequentially dense subsets of R. So a subset S of R is said to be sequentially dense if and only if every real number is the limit of a sequence in S. So if I can find a sequence in S that approaches any real number, for every real number, if there's a sequence in S that approaches that real number, then we say S is sequentially dense. Now, the interesting thing is that these two notions, sequentially dense and dense, are in fact equivalent. Okay, so we're going to go over the proof of this one, and then we'll do an example on that. A subset of R is dense if and only if it is sequentially dense. Okay, so this is an if and only if statement, which means we would have to prove two different statements, two different if-then statements. The first one is the forward direction, which is if a subset of R is dense, then it is sequentially dense. So I'll start with assuming that subset S is dense. So let S be a dense subset of R. Looking at the definition of sequentially dense, what I need to do is to show that if I take any real number, an arbitrary real number, then I can find a sequence in S that approaches that real number. So let R be in R. So that what I'm looking for is a sequence Sn in S, and I'm going to do the scratch work on the right, that Sn approaches R. So this is the objective. So how do we do that? What we would like is we would like Sn minus R to be small. So we can just make sure that Sn minus R is, let's say, less than 1 over n, because 1 over n goes to 0. Therefore, if I make sure that Sn minus R is less than 1 over n, then I would be done. And this can be done because if I rewrite this inequality, I would get this inequality. And of course, I can always find a real number inside any interval. An element of S inside any interval. If you go back and look at the definition of dense, that's exactly what it was. So let's now formally turn it into a proof. So for every positive integer n, consider the interval r minus 1 over n and r plus 1 over n. Since S is dense in R, there is some Sn inside S that is also between r minus 1 over n and r plus 1 over n. So this means Sn minus r in absolute value is less than 1 over n. Now, we know 1 over n goes to 0 by in fact that was an example. by an example. This was the first example we did for convergence sequences. 1 over n approaches 0. Now, note that Sn minus r is less than, if I want to use the comparison lemma. I'm going to write it down in the form of the comparison lemma, which is some constant sequence minus its limit. So now I can apply the comparison lemma. By the comparison lemma, Sn converges to R. So every real number that I take, it's the limit of a sequence in S. Just to remind you, comparison lemma was this. I have a sequence an and I have a sequence bn. I know bn approaches b, and there's a constant c that this inequality holds after some point. And if that is the case, then an would also approach a. So this was the forward direction. So the backward direction, for the backward direction, we're going to have to assume that a set is sequentially dense and show that it is in fact dense. So let S be a sequentially dense subset of R. What I need to show is that this set is in fact dense. So suppose a less than b are two real numbers. So let's just step back. Why am I taking two real numbers? Because I would like to show that S is dense. So in order to show it's dense, I would need to show in every interval there is an element of S in every open interval. So what I need is I would have to take the interval from A to B and then shows there's something in S that is inside this interval. Well, that would have to be the case, because if you take some point in here, elements of S would have to approach this point. And if they are approaching this point, they would have to be inside the interval at some point. Now, the most natural number to take inside the interval would be the midpoint. So since S is sequentially dense, there is Sn in S such that Sn approaches the midpoint, a plus b over 2. Now, I would like to show that at some point the sequence is inside this. So in order to do that, I will have to take the epsilon to be this length, or half the length of the interval. Let epsilon be b minus a over 2 in the definition of limit. So there is some natural number n such that for every natural number n, if n is at least n, then Sn minus the average is less than b minus a over 2. Sn minus the limit is less than epsilon. This tells us Sn is less than b minus a over 2 plus a plus b over 2 and a plus b over 2 minus b minus a over 2. And this tells us Sn is, on this side we get, on the right we get b, and on the left we get a. So that means Sn is in S and it is in the interval a to b. So this means S is dense, because we were able to find some element of S that is inside the interval AB for every interval. Okay, so this is really useful when we're dealing with the sets that are dense. You could switch back and forth between being dense and being sequentially dense. So here's one example. Every real number is the limit of a sequence of rationals. Also, every real number is the limit of a sequence of irrationals. So essentially we have proved this one before. So we know Q is dense. So now by theorem, the theorem right before the one that we just did, theorem 2.6, Q is sequentially dense. Thus, by definition, every real number is the limit of a sequence in Q. And that's the end of the story for the first part. And then similar for Q complement. Similar argument works for the set of irrationals, or in fact for any dense subset of R. Okay, so this brings me to the end of this video. If you'd like to continue with these videos, feel free to subscribe to the channel.